In this video, we're going to be going through the easy questions for bulk properties of solids. As usual, use this video to either mark your work or to help you with any of the questions you were stuck on. Question 1a is to define the density of a material. We covered this in one of the earlier topics, but it's always worth revising. Density is mass per unit volume of an object or a material. Question 1b. A student takes an empty measuring cylinder and places it on an electronic balance. She records the mass and adds an unknown liquid to the measuring cylinder. She records the volume of liquid in the measuring cylinder and the reading. She repeats and plots her results on the graph as shown in figure 1 below. So you may remember we did something similar to this in year 10. First bit is for part B is to determine the mass of the empty measuring cylinder. That on our graph is going to be right here before we've even started adding the liquid. That'll be the mass of your empty measuring cylinder, and that is 60 grams. Before we move on to the next page, the next question is about to ask us to work out the density. So I'm going to show us which point I've used to get my measurements for density. Any of the points would be okay, but I tend to always use the largest one. So if we read off the graph, at that point we've got a volume of 100 centimetres cubed and a mass of 140 grams. So question 1c, we've got 4 different liquids and their densities, and we're going to use the graph that I just showed us, how we're going to use it to work out the density of this liquid. So first of all, we've got a volume of 100 centimetres cubed, and we've got a mass of 140. That's being read straight off the graph, but we did just work out the mass of the empty measuring cylinder, so our liquid is only 80 grams. All of the measurements for density in the table are in kilograms per metre cubed, so we do have to convert these. So 80 grams into kilograms, we are going to divide it by 1,000, so we'll get 0.08 kilograms. For our volume, we need to convert it into metres cubed, and we've got it in centimetres cubed, and what we're going to do is we're going to divide it by 1 times 10 to the 6, and we'll get 1 times 10 to the negative 4 metres cubed. If you're unsure about whether you're going to times or divide with the conversion, just have a think, is your number going to be bigger or smaller when you're finished with it? And if we're converting from centimetres cubed to metres cubed, we're going to have less metres cubed, so we're hoping our number's going to get smaller, which it has. Then to calculate our density, we're going to do 0.08 divided by 1 times 10 to the negative 4, and you should get 800 kilograms per metres cubed, which if we have a look up here, that means we have ethanol. And then question 1d, draw a line on figure 1 to show the results you would expect to obtain from this second liquid. It's a lower density, so it's going to be a lower line. This is what our lower line would look like. It would start at the same point because the measuring cylinder stays the same, but it would increase at a lower gradient because it is less dense, so there's less mass per unit volume. Question 2 is about a cable car, and we've got a variety of different extensions as we add load to our cable. Part A, we need to describe how we would calculate the extension in this experiment. So the way we do it, I've put it as an equation, but you could have also written it as a sentence. To work out the extension, you do the total length with your load applied, but you take away the initial length with no load applied. So if you were writing that like a method, the first thing you'd do is measure the length of your wire without a load, and then during your experiment you'd add a load, but because we're working out the extension, you need to make sure you take away the initial length of the cable at each measurement before you write it into your table. 2b is asking us to plot the data from the previous page. So I've already plotted it for you, but I thought we'd draw the line of best fit together. So this first bit we can see is a straight line, so you'd need to use a ruler, but after that it is a bit of a curve. So I'll do my best attempt at a curve here. You can use a ruler and just bend it slightly, but after this point, our cable has gone past the limit of proportionality, which means it's not proportional anymore. It's not going up in a straight line. So the next question, 2c, says to mark with a letter P the limit of proportionality. So it is here, right in there above the 2 meters and at 4 times 10 to the power of 5 newtons. Question 2D on the next page then asks you to use your graph to determine the maximum load before it breaks. So when it breaks, that's our final point on our graph. And we're just going to read back from our graph here. So it's 4.7. So using our graph on the previous page, we knew the max load is equal to 4.7 times 10 to the 5 newtons. Don't forget that times 10 to the 5. It's hidden on the label up the side. And then from that, we can do the next part to calculate the breaking stress. So that's part I. But part I, let's think what else we've got. We've got the area here, which is 2.5 times 10 to the minus 3. And the equation we're going to use is stress is equal to force divided by area. Our force is going to be our maximum load, and the area is our cross-sectional area. And the answer is 1.88 times 10 to the power of 8. And you can do for your unit PA for pascals or newtons per metre squared, both of which are acceptable, but make sure you remember to put one of them. Question 3 is about Hooke's law. So the first one is to state Hooke's law. This definition comes up a fair bit, so I suggest you try and remember it. The first part is the extension of the material is directly proportional to the applied force or applied load, and you need to state the second bit as well, up to the limit of proportionality. So that means if you were to load more on a material, it would no longer extend proportionally. In 3B, we've got a bungee jumper of mass 65 kilograms, and they start with a rope that's 25 meters and it stretches to 32 meters. First part is what force does the bungee jumper apply? That is just his weight. So mass times gravity, 65 times 9.81. That's 637.65 newtons. Or if we round it up to two significant figures, just like the question, 640 newtons. Part 3C is to calculate the extension of the rope when it's fully stretched. So we take our fully stretched length and we take away the initial length just to get the extension. So it's 7 meters. And we're going to use that answer and the weight from before to calculate our spring constant. So the equation we're going to use is force is equal to K, which is our spring constant, times our extension, which I'm going to use an X for here. And we're going to rearrange that. So K is equal to F divided by X. So our force is going to be his weight. I'm going to use the full value, not the rounded up one. And we're going to divide that by 7. And you'll get 91.09 newtons per metre. So N/M. And I'm just going to round that to two significant figures again. 91 newtons per metre. Question 4A. Figure 1 shows an incomplete extension load graph obtained by adding 1 Newton weights to a spring and recording the extension. The spring obeys Hooke's law up to point A. Draw a suitable line to show this. So if it obeys Hooke's law, we are going to get a straight line because it's going to go up proportionally. So every time we add a bit of extension, the force will go up by the same amount. And then question 4B, state the relevance of point A. That's our limit of proportionality. If we were to go beyond this, as this graph does, Hooke's law does not apply. It's not a straight line anymore. 4C, use figure 1 to calculate the energy stored in the spring when it is extended 8 centimetres. Show you're working clearly. I'm just going to draw the area under our graph. So if I was to turn back, you could see it on there. So what we're going to do is we're going to use the area. So it's half times the width times the height. So half times the extension times the force. Half times 8 centimetres, don't forget that, times 12 newtons. And we're going to convert this into metres so that our answer is in a nice unit. So I'm going to divide it, just put it in brackets, divide it by 100 because there's 100 centimetres in a metre to get this in metres, times it by 12. So you'll get the energy that is stored in the spring is 0.48 joules. Question 4D. Up to point B on figure 1, the spring exhibits elastic behaviour. State the relevance of point B. So B is just beyond point A. but it's already started to curve, is the elastic limit. So up till A was the proportional limit, where it's going to be a straight line. B is the elastic limit. Up until this point, the spring is still elastic. It will return back to its original length. If we stretch it beyond B, it will no longer go back to exactly the length and the shape that it was before. 5A, a student applies a range of forces to a metal wire and records the extension. The force extension graph of the results is below. Mark the elastic limit on figure 1 and label it E. So it's this point here that I'll label E now, and it's at the end. It's just beyond where our straight line ends. So if you have a look, our limit of proportionality is a little bit there. I'll put a little P on it for proportionality, but E is just a little bit further where it starts to curve. And show clearly the range of forces which cause the wire to exhibit elastic behaviour. That's any force beneath E. If we were to add more force, it would be plastic behaviour. It would start to change shape and not return. Question 5B. After they've added the 15 newtons, he reduces it in small increments and records what happens to the extension. Draw what the relationship would look like. So we would get a straight line going back, but the curve doesn't reverse. So what happens is, because we've stretched it too far, there's now plastic deformation, and at the end, let me just show you where the end would be once I've taken all the weight off, just here. It just wouldn't go back to the original length that it was. It would be slightly deformed. On to our final page. Question 5C, state the definition of a brittle material and a ductile material. So brittle materials fracture with little elastic deformation. So there is little or no plastic deformation. So that means they're very easy to fracture or break. Whereas a ductile material can deform plastically. They can be drawn into wire. So they stretch before they break. And the final question, figure 3 shows a force extension graph for a brittle and a ductile material. Label them as brittle or ductile. So the first one is a brittle one. So it stretches and then it breaks quite quickly. There's no plastic behaviour there, or there's a very small amount of plastic behaviour there. And then the last one here is a ductile material. It gets to its limit of proportionality around here, elastic around here, and then it keeps going, deforming slightly.